Okay, so I want to look at in this video some things about vectors, kind of formalize things about vectors and speed and acceleration and things that you probably already know, but like I said, just as kind of collecting it and putting it all together and maybe also showing you some of the notation you might see on the AP exam. And I do want to talk about this warm-up, even though this warm-up really doesn't have anything to do with vectors directly, but it does talk about representing motion, a position, a velocity, and acceleration. So I thought it would be a good place to start. You can probably solve a lot of this without even watching me go through the video. So certainly feel free to do that, and then check at the end of the end of this portion of it to see if you did them right. But or you could follow along, doesn't matter. But when I'm looking for velocity and I'm given a position graph or a position function, then I know that its derivative would be velocity. So the derivative of the position would be velocity. And it's a very easy derivative compared to some of the things we've done in the past, right? So the derivative of just a polynomial would be 3t squared minus 26t plus 35. And then its derivative, right? So for part B, if we do the derivative of our velocity function, we would get an acceleration function. So then that becomes 6t minus 26. Okay, now part C seems to be a question that comes up quite a bit on the AP exam, and in a variety of different ways you could ask it. Is it speeding up? Are you analyzing, a graph or an equation or maybe both? But the key to determine is it speeding up is looking at the signs of the velocity and acceleration. So I need to determine what is v of 5 and what is a of 5 and compare their signs. Because if the signs match, if they're both positive, it's speeding up to the right or up, whatever that positive direction is indicating. If they're both negative, it's also speeding up, just in the opposite direction. But if the signs are opposites of each other, that's how you know it's slowing down. So v of 5 would be 3 times 25. I'm just plugging it into the part A, minus 26 times 5 plus 35. So you could compute that, and I believe you should get negative 20 for its velocity. It doesn't give us any dimensions, so we just have to leave it unitless. Now, a of 5 would be 6 times 5 minus 26, which is 30 minus 26, which is 4. Now, more importantly, our velocity is negative and our acceleration is positive. So I can make a conclusion that this is slowing down. And the direction that it slows down is always based on velocity. So this is slowing down to the left. So I could say at t of 5, is it a particle? Yeah, sometimes it's a particle, sometimes it's an object. So at t of 5, the particle is slowing down. And your justification, we showed the work. All you just to say is since v of 5 is negative, but a of 5 is positive. Okay. Next one, writing things that represent total distance. So when you have a position function and it's just moving, like let's say on the x-axis, which this one was, and I probably should have started the video emphasizing that. But if you're just moving along the x-axis, so like you maybe go forward for a while and go backward for a while, and you might be just going back and forth, and not tell, like, if here's your start, here's your end, how far did you really truly travel? Because if you just look at displacement, your displacement would be your final position minus your starting position. It doesn't account for all the back and forth. But if you want total distance, you need to account for those negative values, right? So we need an absolute value to represent that. And so a total distance, what we can do is we can look at this velocity function and we can accumulate the change of that velocity. So my total distance is going to be the accumulation from, what did it say for the first, from 2 to 8. So from 2 to 8 of not just the velocity function, but we really want to take the integral of, oops, that's a 35. We want to take the integral of speed. So we need to insert absolute value. And I'm going to fix that 3 because that's really embarrassing. Plus 35. Okay, so there's an expression that would represent the velocity. Sorry, that would represent the total distance traveled. Now, it does say we can use our calculator to solve this. So there's a way that you can type this into your calculator with these absolute value bars. And so you want to find your operator ABS. And for most calculators, it's under the math operation function. So you hit math. And then if you arrow over to number, you would see that. And then in fact, I can show that to you. Let me flip my screen around here. It'll take a second for this to catch up. There we go. So let me go ahead and pull up my Chrome. If you look at, there we go. I have my calculator right. I think, is it here? Nope, here. Nope, here. Nope, here. Oh, this is exciting. Oh, how about this one? Nope. Well, I had my calculator, I promise. Oh, there it is, over in Honors Pre-Calc. Wow, that worked out great. Okay, so let me quit that for a second. So yeah, math, arrow over to number. Oops, there it is. Arrow to number, and there it is, absolute value. Okay, so long story short, we could type that in, and we would get 84. Okay, so sorry about that. So 84 is not the displacement. 84 is the total distance traveled. So that'll accommodate for both, like going forwards and backwards, and add that up. Okay. Now, there it is, 84 units. Okay. The very last piece is asking for average velocity from 1 to 5. And so for average velocity, so that it's not speed, right? So we want our velocity function. So we're going to accumulate from 1 to 5 our velocity function to get us the displacement. And so I could even just say v of t, since I already have defined what v of t was. But then I want to find its average. We can divide over the interval from 1 to 5, which is 4 seconds or 4 units of time. And so then I would type that into my calculator, no absolute value needed, and I would get -12. And then a lot of times they want you to label that, but we don't know what the units are or the dimension of time, but realize that it is a velocity measurement. And it's okay to have velocity being negative. It just meant, on average, you're over the 4 second interval from 1 to 5, your average velocity was -12, meaning you, on average, were moving to the left at 12 units per time. Okay, so other than that weird computer glitch, aka Mr. Brown error, hopefully that was okay on that warm up. So then maybe I'll look at just some things about vectors here, and I'll probably pause the video and create a second one for the backside of this worksheet. But the AP exam likes to use this notation, these kind of like these arrowheads as parentheses, like in place of parentheses, I should say, to indicate vectors. And I know last year in Honors Pre-Calc, sometimes we use letters I or J or K, depending if it's a 3-dimensional vector or not. And so we'll look at an example like that too. But if you see those bracketed things like this, that's indicating a vector. And so these are vector valued functions. So f is a function, and each of the components represents a two components. So it's a 2-dimensional vector in time. So, it's not super hard once you kind of decode it. So it says, okay, draw the path of the particle from time equals 0 to time equals 4. Well, this vector, this t is representing all of the possible x, locations, and this t-1 squared is representing all of the y locations. So some vector value functions that are given in terms of time can easily be translated back to the xy, just xy coordinates. This is one of them. If every x is just equal to t, then certainly we can just input that into that t value, and now we have a function that is not in terms of time. It's just y is equal to x minus 1 squared. So like that might be a really good thing to do for part A when we're drawing the path of this particle from 0 to 4. Simply because we can represent that, again, our function was y equals x minus 1 squared. I can, quite quickly graph what that looks like from 0 to 4. And I know this is going to be a parabola. It's going to be touching the x-axis at 1, 0, because that's the vertex. And at 0, it's there. So like 0, that would be 1. At 1, it's 0. At 2, we're back to 1. If you're doing table of values, 3 would be 4, and then 4 would be 9. So like it's up just up here, just part of a parabola. So there's our path. At 4, we're at the height of 9. Now those are just x, y components, not necessarily time components. Okay, part B, find the value of f of 2 and the derivative of 2. And remember, these are vector valued functions. We want to give it in that, in that notation. So f of 2 as a vector, put that little hat on it, right? That little arrow. You just put 2 into each of the components. So, and then we'll leave it in vector form. So 2 is just 2. And then 2 minus 1 is 1. 1 squared is 1. So the vector that represents time equals 2 is 2, 1. And then the derivative, so before we find the derivative at 2, it might be helpful to write the derivative as a vector valued function. And so you just do derivative by the components, which is really easy and nice. Derivative of t is 1, and the derivative of the y component would be 2 times t minus 1 to the first power, chain rule, just a 1. Or if you would have expanded that out to t squared minus 2t minus plus 1, you get 2t minus 2 is the derivative. And then the derivative vector, particularly at 2, would be 1, 2. Okay, so then there's that. And then part C says, let's draw that vector. And so when we draw that vector, we're the first, like if it doesn't say where to draw it, we draw it as a position vector, and the position being 0, 0. So we want to go from 0, 0 to 2, 1. And so here's 0, 0, 2, 1. Well, it basically, if like vectors have a direction and a magnitude. Well, basically the direction says if I'm starting at 0, 0, it's going to point to where, right? Where are you at? That's t equals 2. That's where I'm at that spot. So I should probably erase this arrow not to get confused with the vector. But at t equals 2, I'm at that spot right there. And the vector goes, there's a tip and there's a tail. So again, maybe I'll do this in blue just to highlight that. So we're going from 0, 0 to 2, 1. So that's our vector. It should look like an arrow. And then part B, or the second part of that says, draw the velocity vector such that the tail of it is at the head of the position vector. And so this vector of 1, 2, so it, if I draw that as a position vector, wherever I'm starting, it's going to get me to the next position. Well, 1, 2, like wherever you start, it would be like, okay, go over 1 and go up 2, aka like a slope of 2. So then that vector would look something like that. So I want to take that vector and just put it on, if that represents over 1, 2, I would just put that right there. And so that vector, that purple vector, is really going to represent the slope of the tangent line, because that's what velocity represents. Okay. And then let's go ahead and it's very similar for example 2. It's even something where you could pause the video and do the calculation and then check it at the end. But it's very similar, right? Draw the path from 0 to 2. So again, this could represent our x. So our x could be 2t. This right here could represent the y. So y is t squared plus 4t. We just maybe do a quick division here. So every t is equal to x over 2. And then we would substitute that into our t values there and there. So let's do that. We'll go ahead and rewrite that as part A here. Oh, well, first, yeah, so I'll first get the equation. So y equals x over 2 is a quantity squared plus 4 times x over 2. Well, that is it's still going to be a parabola, so it's like 1/4 x squared plus 2x. So there's our our function in terms of x, and we can sketch that, or think about like from 0 to 2, just knowing what those values are as well. When t equals 0, our value will be 0, 0. So when t equals 0, we'll get 0, 0. I don't know why I'm doing that table over there. No idea. So let's erase it. And then when I know t equals 2, I'm going to get 4 comma 8. So at least I know those values, right? Because 2 times 2 is 4, and 2 squared is 4. Yep. Okay. So the path then, if I were to graph that, 1/4 x squared plus 2x, you could complete the square if you wanted to get its vertex. So y equals 1/4. So we get x squared, and then actually becomes 8x, and then plus 16. And that's really a plus 4. So we subtract 4. So like if we wanted the whole parabola, y equals 1/4 x plus 2 squared, x plus 4 squared, and then minus 4. So the vertex is at negative 4, 4. And so when I draw that, so I go 1, 2, 3, 4, 1, 2, 3, 4. So here's where the vertex is. So, and I do know it goes through 0, 0, and and I do know it went through, I think 2, 8. But in terms of just our path, we're not going to see a lot of the parabola, right? Like, because this we're not going to see, so leave it dotted. It's very wide because it's a coefficient of 1/4. So we really only see starting here and moving, in this direction. So like that yellow part might be all we see from 0, 0 up to 2, 8. Okay. And then for part B, let's find those other vectors. So that we, h of 1. So if we look at the components, h of 1, the vector at 1 would be 2 times 1, which is 2. And then 1 plus 4, which is 5. So I'd want that vector. So if I'm at 1, then I want to go. So, and remember, 1 would have been, so 1 is 2, 5. So I didn't plot that point. It'd have been right there. So my vector would be pointing, how do I get to that spot? So there would be the vector 2, 5. I'm going over 2, over 2 up to 5. That would be where position 1 would be. And then I'm looking at this, I'm like, there's something wrong. You probably already saw that. That should be 4, 8. I'm like, wait, what? There's something wrong here. Sorry about that. There we go. And so then that makes sense. So to get from 0, 0 to the first position, you go over 2 up 5. Ooh, there it is. And then the derivative, let's go ahead and write that as well. And then, hopefully that makes sense. I would find the derivative first, and that is just the vector 2, because the derivative of 2t is 2, and then it's 2t plus 4. And then the vector at 1 then, so h prime at 1 would be the vector 2, 6. So that again means go over 2 and go up 6 units, or a slope of 3. So if I draw that as a vector, and I just want to put tip to tail, I could put that vector right here at the end to represent really the derivative at that point. Okay. So again, most of that probably is familiar to you. Maybe the notation is a bit different, but the concept behind it, I'm hoping, does make sense. So then what I'll do is I'll go ahead and go through the back page in the next video, just to kind of, again, just go through a few more examples of what you might see on the AP